What is meant by, how would you say that? I mean, v prime of r, but how would you say that as a rate? Which one? Yeah, okay, you always start with the rate of change of blank with respect to blank. It's always going to be the rate of change of the output, so volume, with respect to whatever the input variable is, right? So if you write it as a ratio, it would just look like that, dV dr, right? So I want you to make that connection. Whatever the variable is that's inside the function, the independent variable or input variable, that's the variable of differentiation, and it goes on the bottom. Okay? Whatever the output variable is, that's the variable that goes on the top, right? So we're looking at the rate of change of volume with respect to radius, and what is the answer? You can do that derivative. No. 4 pi r squared, right? How come? Because we've got some constant out front that we just leave there. The derivative of r cubed, that's an r cubed. We bring the 3 down front, and then we just subtract 1 from the exponent. Okay, there's something really amazing going on there, by the way. Why is that incredible? It's pretty cool that that's your answer. The rate of change of the volume of a sphere, right? This is a sphere. The rate of change of volume of a sphere with respect to radius is what? It's what is that? 4 pi r squared is what? That's an important quantity for a sphere. What is it? No. No, I mean, but it's a sphere. But that defines an important attribute or property of a sphere. Not circumference. Well, what would the units of that have to be? It's an area, isn't it? We know that. Say it again. If it was circumference, it couldn't have an r squared in it, because that would just be the line around it, right? That would have to be something linear, because the dimensions would just be like meters, if we're right. This is going to have to be measured in units of r squared, which would be meters squared. So it's got to be some kind of an area. It's the surface area of a sphere. Okay. Ponder that one, and there's some real insight there. I mean, that gives you some real intuition. The rate of change of the volume of a sphere is equal to its surface area. Well, I mean, you can kind of play a little animation in your mind there. As the sphere grows, what's the only part that you can see? The surface, right? And so as the sphere grows from one radius to a slightly bigger radius, where is that extra volume being added? To the outside, to the surface, right? Oh, interesting. So the rate of change of the volume is equal to the surface area, because that's where the extra volume is being placed. Interesting. Interesting. We'll come back and discuss that in way more detail much more towards the end of the year, but that's pretty interesting, right? The math gods are wise. You should always try to listen to what they're telling you, because it's not just some meaningless equation. That says something pretty profound about the way that a sphere grows. Okay. So rate of change of volume with respect to radius. Okay, so if we flipped that around and we said dr dv, that's going to be something different, right? Dr dv, it would end up being the rate of change of radius with respect to volume, and that would be something different. Okay, we don't need to go into that in any more detail for now. I want to look at some kinematic stuff today. Okay, so derivatives as rates of change. kinematics is an awesome example of thinking of derivative as a rate. So let's remind ourselves what the important quantities are in kinematics, right? We have the position is going to be, we're going to call it S of t or X of t or whatever you want to call it. We like to use S because position doesn't necessarily have to only be on a line, right? I mean, it could be, things could move through three-dimensional space in some way that's not a line. We'll make ours pretty simple. So the stuff that we're going to consider will be motion on a line. Velocity is the rate of change of position with respect to time, so the derivative, right? Derivative of position, and acceleration is the derivative of velocity, which we now know is also the same thing as the second derivative of position, right? Okay, so let's look at a cool example here. Suppose the position of an object moving horizontally after t seconds is given by that position function. So that might as well be an x because it's going to be an object moving horizontally along a line. So we wouldn't even have to call it s. We could just call it x on the x-axis, but we called it s. So the position is given by 24t minus 4t squared, and what does that mean? Okay, so that's the domain, right? That's the domain because that's the set of values, input values that we're using for this function. So that's kind of a real world thing because that means that this is going to be only true from 0 to 8 seconds. After 8 seconds, maybe it does something different, right? But for the first 8 seconds, that's the position function that models the position of some object. So again, like let's say we're going to start where the middle of the board here is 0 on our x-axis. What's the initial position of that object? 0. How'd you get that? Yeah, you plug in t equals 0 and you just get 0, don't you? Everybody see that? What's the position after 1 second? 20? Because s of 1 is 20, right? Okay, good. So get the idea. So let's find the other kinematic functions first of all. So if we know position, what would be the next one we'd calculate? Okay, what is velocity, everybody? Oh, velocity is going to be derivative of that. So 24 minus 8t, right? Because the variable of differentiation is t, so we're differentiating with respect to t. We're just using power rule, right? So there's velocity. Okay, now what do we calculate? Okay, what's acceleration? -8. It's constant and it's -8. Okay, good. Okay, so I would like you to determine the velocity and acceleration of the object at t equals 1 second. Okay, this is pretty cool that we can do this, right? We've got all these kinematic quantities now are functions of t, right? So we could say, in math we'd say they're parametric equations in the parameter t. So that means t is what links them all together, but here's how you think about it. Remember our special video camera. When we're filming something going on at the front of the room, when I'm walking along this line, and you're filming this with a video camera, you're just looking at the index, you know, the time index of the video camera. If we pick a certain value, t equals 1, well, there's going to be one frame in that video corresponding to t equals 1 of this movie that's going on at the front of the room, right? We have this special calculus camera, which does something unique. Not only are we able to look at this thing and see what the position is at the front of the room, because I'm walking along, so, you know, say we've got some hash marks along the front so we can see position. It also has the ability to read out instantaneous velocity and instantaneous acceleration, right? So we need to calculate what those are going to be. At that one frame in the video, at t equals 1, what would velocity be? 16 is right. How did we get that? Just evaluate v, absolutely. So we're just evaluating v of 1 equals positive 16. So after 1 second, what does that tell you about the object moving horizontally? Which way is it moving? Go ahead, to the right, positive direction, with a magnitude of 16 whatever. And we're measuring t in seconds and s in feet. So what would the units be? Feet per second. Okay, what would the acceleration be at t equals 1? Negative 8. Yeah, right? Because it's always negative 8. What would the units of acceleration be? Feet per second, change in velocity over change in time, right? So velocity is measured in feet per second, time is measured in seconds, so it'd be feet per second per second. Interpret that. What does that mean? Negative 8 feet per second tells you what about the motion of this object? It's, well, okay, slowing down initially, right? But after a while, it may not be slowing down. Think of it in terms of the invisible hand. In which direction is the invisible hand pushing? Right? And we know that because acceleration is proportional to force, right? What causes acceleration is force. So to get an acceleration of negative 8, that means the force must be pushing me in the negative direction. So initially that means the hand is slowing me down, but at some point it's going to actually be speeding me up in the negative direction. Okay? So what that really means then, an acceleration of negative 8 means that every second the velocity is increasing in the negative direction by negative 8. If I start off with a positive velocity, that just means I'm losing some positive velocity, right? If I'm already traveling with a negative velocity, it means I'm getting more negative velocity, that much more every second. Okay? Give me thumbs on that. Is that making sense? Okay, so let's answer some questions then. Determine the position and acceleration of the object when its velocity is 0. How are you going to petition the math gods for this information? How do you know 3 seconds? Okay, right. So we need to know, first of all, when the velocity is 0, we need to know what time is that. We need to know what frame is that in our video. Okay, which equation are we going to use to determine when the velocity is equals 0? The velocity equation, because that's the equation that links velocity to time, right? And all we'd have to do, is just set that equal to 0. So v of t is 24 minus 8t, and we're just going to set that equal to 0 and solve, and that's a pretty easy thing to solve. We just get the solution t equals 3, okay? So now that I know t is 3, how could I calculate position? Plug it in. What that told me is the frame in our video is the t equals 3 frame, and I can use my kinematics equations to figure out what the values of the other kinematic quantities are at that frame by plugging in t equals 3. Okay. So we'd get s of 3 just equals what? 72 minus 36, so 36. What would the units be? Feet, okay. How about acceleration? It's always negative 8. And feet per second, oh, we never wrote that up there, did we? Feet per second. How do we, that's kind of an awkward thing to write. Yeah, so instead what we just say is feet per second squared. But that's what it means, is feet per second per second. Okay? Give me 1 to 5. How are we doing on that? See the process there? To answer a question like that, determine the position and acceleration, we need to know the time. Okay, so we had to use the velocity equation. Okay, what about this one? When is the object moving right? Okay, how would we answer that? Okay, but you're right. So you could, so the suggestion is you could reason that we know that t equals 3 is when the velocity is 0, so it's going to have to be, that's going to have to be the point when it changes, right? And then you guys are reasoning that because it starts off with positive velocity, it must be moving to the right up to that point. Okay, we can make it simpler though. We don't even have to do all that thinking. We'll just use an inequality instead. How could I set up an inequality here that's going to give me the answer directly without having to do any inferring or reasoning? When is the object moving to the right? When the velocity is what? Okay, when it's positive, yeah, right? So when the velocity is greater than 0. So we could just ask ourselves, if we have this velocity function, velocity is 24 minus 8t. So moving to the right would just be when 24 minus 8t is what? Greater than 0, when the velocity is greater than 0. So we just solve. Okay, well, if I subtract 24 and divide by negative 8, what's that going to give me? It's going to flip that sign, right? I'm going to get negative 24 divided by negative 8. Am I just going to get that if I solve that? How about that? So t is less than 3. Now, our domain starts at 0. So when would the object be moving to the right then? When t is what? Okay, and I could include 0, right? Because at 0 it is moving to the right. So moving to the right when t is greater than or equal to 0 and less than 3. What about at 3? No, okay, at 3 it's not moving to the right. That's when its velocity is 0. Okay, so there's when it's moving to the right. I mean, what would my similar strategy be for determining when it's moving to the left? I'd want to know when the velocity is, say it again, less than 0, yeah, negative, right? And I would just solve that equation. If I did that, moving to the left, I would just ask the question, when is 24 minus 8t less than 0? And of course, I would get the answer, t is greater than 3 this time. And because it ends at 8, the domain ends at 8, it would be on the interval t is greater than 3 and less than, or was it 8? Is that what it was, or was it 10? It was 8, yeah. Less than or equal to 8. Okay? Give me 1 to 5. Does that make sense? Okay? All right. Easy stuff, right? On what intervals is the speed increasing? How come?
Well, when you say like it's speeding up, it's going the other direction, and it's a vector quantity, so it's negative.
Okay, is speed a vector quantity?
Velocity.
Velocity is a vector quantity. Is speed a vector quantity? No, speed's a scalar. Speed is the magnitude of velocity, right? Remember, when you're driving in your car, you don't have a velocitometer. That'd be very confusing. You have a speedometer. You don't want your velocitometer to tell you you're traveling negative 70 miles an hour when you're going to Portland and positive 70 when you're going to La Grande, or some weird combination when you're going someplace else, right? We don't want that. We just want to know what the magnitude of velocity is, which is a scalar. It's always positive. So when is the speed increasing? How are we going to know? Okay, it is going to be after 3. You're right. But how could you justify that? What has to be happening, think about this now, in terms of the invisible hand. What has to be happening for your speed to be increasing? When would your speed be decreasing? Oh, by they, what do you mean? Okay, choose your words more carefully, because it's not forces. We're talking about kinematic quantities here. Force is associated with acceleration. But your speed is going to be decreasing when what happens? It has to do with acceleration, and it has to do with velocity. But I want to know what would be the condition under which, for velocity and acceleration, under which your speed would be decreasing. Let me say that again. That's a lot of words. You got to really focus on this. What would have to be true of the velocity and acceleration for the speed of an object to be decreasing? It must be higher? Not higher, not necessarily higher, but something has to be true. No. And it's not the magnitude. The velocity could have a larger magnitude than acceleration, or vice versa. That's not it. That's it, if they're different signs. Everybody get that? Let's think about what that means. If velocity is positive, right, what would the invisible hand have to be doing to slow me down? It'd have to be negative, right? So therefore the acceleration would be negative. Positive velocity and negative acceleration means slowing down. Okay, what if my velocity is negative? What would the invisible hand have to be doing to slow me down? Pushing in the positive direction. So as long as acceleration and velocity are opposite signed, then I know I'm going to be slowing down. So I'd be increasing my speed then under what condition? When is the speed going to be increasing? Yeah, exactly. When the invisible hand is helping me along, right? When it's pushing in the same direction as the velocity. Okay, so then all we have to do here is figure out when the velocity and acceleration are aligned, when their signs are aligned, right? When they're either both positive or both negative. Okay. Well, this is made pretty easy because we already know something about acceleration. What's the sign of acceleration always? Negative. Okay, so then the only time when we could be speeding up would be when the velocity is negative, right? Which we already, no, we don't know, but we can find out. Actually, we do know, don't we? Oh, let's see here. Yes, okay, right, we know that, right. We did that in the last problem. I was looking up here. Yeah, so we want to know the velocity is negative when the object is moving to the left in the direction of the acceleration, right? So that would be the green case, okay? So for our notes, okay, make sense? Okay. So kinematics is really just differential calculus, isn't it? I mean, it's when you do kinematics in physics, that's really what you're doing. Okay, now here's a really interesting case. Okay. So El Capitan, have you guys ever been to Yosemite? Ever been to Yosemite? El Capitan is pretty amazing. It rises vertically, nearly vertically, about 1,000 meters from the floor of Yosemite Valley. It's pretty amazing. You can stand on the top of El Cap and you can look down, and it's pretty incredible. Assume you shoot a bullet coated with slip rim, which is I'm just trademarking. It's vertically upward. You know what slip rim does? It completely eliminates air resistance. Yeah. Okay. You shoot it vertically upward with a muzzle velocity of 1,000 meters per second. Okay, so it leaves the rifle going upwards at 1,000 meters per second. The position function for the bullet, I'm just going to give it to you. That's it, right there. The position function, y, which is the height above the valley floor, as a function of time is 1,000 t minus 4.9 t squared plus 1,000. That's going to predict the height of the bullet as a function of time, okay? So here's our picture. There's El Capitan, and we're just shooting this bullet straight up, and then it's going to turn around and come back down along the same path, okay? How long does it take the bullet to reach its highest point? How are we going to find out? I don't expect an immediate answer, but I want to know, how are we going to find out? How are we going to ask the math gods? A good question here. Okay, everybody agree? It's going to be at its highest point when the velocity is 0, right? The velocity is going to start off being positive and it's going to end up being negative. And we could determine that. If this is the position function, what's the velocity function? Yeah. The derivative of position, which is what? 1,000 minus 9.8 t. Okay, good. Makes sense. So initially at t equals 0, what does that predict the velocity is? V of 0. Yeah, and we knew that, didn't we? It's 1,000. Okay. So it starts off positive. When it's 0 is going to be when it hits its highest point. So we could solve that pretty easily. If we set this equal to 0, so what is that? I don't know. Let's just see real quick. And how do I undo that? Gosh. Oh, there we go. Okay. So 1,000 divided by 9.8 is, there it is, 102.04 roughly. That's how long it takes to reach its highest point. How high does it go? How would I find out? That's it, right? Now we know the snapshot. That's our snapshot at the point when it's at its apex. It's going to be the frame in the video at exactly 102.04 seconds to 2 places, right? So I could just plug that in to y to figure out how high it goes. Y of 102.04 is what? Okay, let's see. Y of t equals 1,000 t minus 4.9 t squared plus 1,000. And so y of that number what did it do? I don't know. That's weird. That's weird. I shouldn't have to add an x to the equation. That's bizarre. Maybe. Yeah, I'm going to call it h. I don't know why it's doing that. Maybe. That's really strange. I guess because y is a variable, maybe. We'll just call it height. Yeah, now it works. Okay. All right. Anyway, we'll pick this up. That's pretty high. Look at that. 52,000 meters. 52 kilometers. You think that's realistic? No, not even remotely.